Good afternoon and welcome to this Scanvac webinar. We will talk today about the effect of energy crisis on the green transition and also power reliability for the HVAC sector. Now when we are living for post-pandemic period, we got the other crisis, we got the energy crisis. And this webinar we are talking about possible measures how we can rapidly implement some kind of energy saving technologies in the buildings and reduce energy consumption. And also we talk about how energy flexibility of the buildings could reduce the demand, because many countries we have a lack of power at the moment. So today's agenda, what we have it here in this seminar, we have here 4 distinct speakers that we'll talk about. We have first talk about the role of potential of buildings and HVAC demand response in the future smart energy system optimization by Kvols Heiselberg. Then the other talk is from Martin Thalfeldt of data-based identification of energy saving possibilities in buildings. And the third speaker is Kenneth Ahlström, who will talk about district heating in the small community. And the last speaker is coming from Finland, Timo Karvinen, will talk about optimization to energy renovation of building stock using artificial intelligence. So next I will shortly introduce the speakers. The first speaker is Professor Kvols Heiselberg at Aalborg University. He is Vice Head of Research and Innovation in the Department of Built Environment. He is a well-known scholar and he's got several awards. He's member of different national and international committees, and his research work covers building physics, ventilation, building energy efficient and zero energy buildings. The second big speaker is from Tallinn University, Martin Thalfeldt. He's assistant professor there. His main research focus of HVAC design, indoor climate of buildings, and ongoing project focus on real-time monitoring and performance assessment of buildings. Third speaker is Kenneth Ahlström. He has worked with energy efficiency since early 1990s. Since 2010, as Energy and Environment Manager and Kopparstaden AB, with amongst other things district heating solution, wind power and various development projects. And the last speaker is Timo Karvinen. He worked with on the simulation, energy relation design and building physics for almost 20 years in academy, nuclear power, software development, and now is working at Granlund company and is involved in energy efficient project development tools for simulation and data utilization. So this is the contents, and I now ask the first speaker of Peter ready, but before that I remind you that you are able to make questions in the chat, and we are going through after each speakers come of the core questions. And in the end of the seminar, we then, if we have time, we also has time to have some small panel discussion. Also, all this video recorded is available later in the Scanvac webpage and also this PowerPoint slides what we are showing here. So, Per, you are the first speaker and floor is yours.
Yes, thank you very much for the introduction. And now, certainly, I'm not able to share my window. I will just try to share my screen, see if that works, and then go to the presentation.
We can see it now, yes.
So you can see it now, so this workaround will work. Thank you very much for the introduction, Risto. The title of my presentation today is The Role and Potential of Building and HVAC Demand Response in Future Smart Energy System Optimization. And the motivation for this talk is that when we look at the both the heat and electric energy sector, with the increased use or increased production by renewables, our energy demand is no longer produced according, or the energy is no longer produced according to the demand, but actually we need instead to change the demand so it fits better to the production. I will come a little bit back to this. Then if you look at buildings, actually they can act as large thermal batteries. So this means there is a potential for creating demand response for both heating and cooling, and also without having too much impact or too high impact on the indoor environment and the occupants in the buildings. And by introducing the demand response, we can actually ensure a more efficient use of the renewable energy produced, because we can manage it better according to the production. And the other advantage we have is that we may reduce peak demands and also obtain a better balancing of the energy system. And I will touch several of these points, or most of these points, during the presentation. As an example, I here show you the development electricity production in Denmark, where we 20-30 years ago had a lot of central units for production of electricity, and today we have a higher and a higher share of wind power in our electricity production. So at the moment we are close to 50% of our electricity production is by wind. So of course this gives a very volatile production, very depending on wind conditions in the space, and therefore our electricity production is very variable. And if we look into the future, this will probably further increase in the future. This is a prediction or calculation of what is actually electricity production costs by different solutions, whether it's a combined heat and power plant based on different fuels, could be natural gas, could be wood chips or straw, in comparison with production of electricity by onshore or offshore wind power. And what we can see here is that these calculations carried out in 2020. So of course, before we had the situation we have today. At that time, onshore wind power was far the cheapest way of producing electricity, and no other, you could say, production methodology could actually compete with this. So therefore, we foresee that our, you could say, centralized or decentralized power plants, of course, they will continue as long during their lifetime, but new capacity will probably be wind power capacity in the future. It's a little bit similar when we look into we have 60% of our houses are delivered by district heating. And if we look at the cost of establishing a new district heating system, we also here can see the district heating production cost per megawatt hour for different solutions. And again here, the solutions with heat pumps are the cheapest solutions to produce heat compared to you could say different types of biomass and natural gas solutions. So therefore, both in the electricity sector, but for sure also in the heating sector, there will be a need for demand response in our buildings. This shows it is an example from 16 showing both for 2 weeks in January, or for January and February, showing the energy use in our system, and you could see here the different days. We have weekdays with a higher consumption than we have in weekends. We have these two power peaks, one in the morning and one in the evening, which are very typical. And the green one shows the wind power production in the same period. And of course, you could also see at that time how price changed in time. So when we have a large part of wind power production in our system, we have relatively low prices. And when the wind power production is low and we are mainly based on fossil fuel production of electricity, then sometimes the price is very high. And actually today we can see the same. We can still have relatively low prices when we have windy conditions and a lot of wind power in our system, while when it's based on gas, our electricity production, then the price level is much higher. In the future, where we will have an increase of wind power, of course, this will be enlarged. So we will have periods maybe with too much electricity in our system, which of course can be exported to other countries. But there will also be periods with too less. So there is a potential in also for the customer, you could say, to move energy use from high price periods to low price periods. If you look at the building as a battery, we have different types of storage in buildings. When we look into the building stock in Denmark, we have a typical storage capacity in our thermal mass of 40 to 90 watt-hours per Kelvin per square meter, and this corresponds to something around 12 to 27 kilowatt hours for a building of 150 square meters. Of course, there is also some thermal mass in the inventory and furniture, but of course it's much less. If you compare this, you could say if you have a thermal storage tank of 1,000 liter, then the storage capacity is about 35 kilowatt hours. So this means in a building with high thermal mass, you almost have the same storage capacity as you have in 1 cubic meter of water. In Denmark, it's typical that you have a tank for domestic hot water of around 200 liters, which corresponds to about 7 kilowatt hours. Then more and more people have electric vehicles, and EV batteries are maybe typically around 70 to 100 kilowatt hours. So actually, if you compare the electric storage in the car with the thermal storage in the building, then of course the electric storage in the car is actually quite high, and these batteries could deliver a large part of flexibility. Then below, I've looked a little bit into what is actually the energy use in a 24-hour period in buildings. If we look in our residential buildings, then the electricity use is typically something between 10 to 20 kilowatt hours per day. So this means it's actually much less than the storage capacity in our car batteries. If we look at hot water use, it's typically 5 to 10 kilowatt hours per day. So this means this 200 liter tank is enough for, you could say, a whole day hot water use. And if we look at our new residential buildings, then the heat demand per day in winter is maybe peaks of around 30 to 45 kilowatt hours, but in average, it's maybe in the range of 15 to 20 kilowatt hours. So this means for many buildings, the storage capacity we have in our buildings can actually provide heating to a building maybe or for new buildings, maybe for at least a 24-hour period. So there are, you could say, big potentials to exploit. We have done different investigations to see even if we have a large potential, will it have any impact on our systems? So the first results I'll show here shows what would be the impact if we utilize the thermal storage in buildings for you could say utilizing this excess wind power we have in periods where the wind power production is higher than the demand. So here in this analysis, we looked at different alternative storage options, both heat accumulation tanks by water and also looking into the passive heat storage in the construction. And then we looked at if we implement this in all the existing buildings where we have oil boilers or electric heating or gas heating and convert them to heat pumps with heat storage options, how much would we then be able to further use excess wind power? And we analyzed different situations, both you could say with water tanks of different sizes, looking into houses with a high passive storage capacity and a low storage capacity, and also looking into how, depending on how large variations we allow in the temperature in the houses, either ±1 degree or ±2 degree. So this is all within, you could say, the typical comfort ranges that we have defined in our standards. The outcome was that actually, if we look into the passive storage and we have maybe the allow a ±2 degree change in the buildings, then actually we could exploit 20% of the excess electricity production we have during in our wind power system, and it's actually almost twice the effect we would have if we installed a 1,000-liter hot water tank in all our buildings. So actually the passive storage can be quite effective. We also looked into the price. So because every kilowatt hour you move, of course you would use electricity instead of fossil fuels. And then the question is, what would be the cost of that when you take into account the investment in the storage possibilities? And it's clear that if you're using the house, it's only a question of investing in a more advanced control system and maybe a few sensors, while you avoid the investment in larger tanks. So it's much more cost effective to use the building as a storage than to invest in a water tank. We have also looked into what is then important for optimizing the storage of buildings, and we did an analysis where we did a simulation study with a parameter variation in order to find out what are the most important parameters for increasing the storage. And the outcome was that the insulation level was by far the most important parameter. High insulated airtight buildings have a much better storage capacity than you could say houses with a high heating demand. And the second most important is, of course, the level of thermal inertia, so the level of thermal mass. And then the third one is the heating system type, whether it's radiators or maybe integrated floor heating systems. Of course, this can be expressed by the time constant for a building, and this is just an example from another paper showing typical time constants in buildings. And of course, you have two time constants. You have one short time constant, which is related to the inventory and furniture and so on in the building, and then you have a longer time constant, which is related to the building construction. And we have done an analysis looking into the building stock in Denmark, saying we have a number of typical, you could say, archetype buildings in our building stock from different times. And here we have been looking at and make some analysis of what is actually the time constant in these different types of buildings. And then we have done some dynamic simulations in order to see these different archetypes, what is what would actually be the demand response potential in these domestic buildings. And there we have, of course, we have not looked at, you could say, the archetypes as they were constructed, but we have identified in our energy performance certificates database, we have actually looked into how does these houses look today, and then we have estimated some ventilation rates, and we have identified the you could say the heated floor area with the energy performance database, and cross-checked with we have a national building and dwelling stock database where all buildings are registered. So we have checked actually to see what is the conditions today for these different buildings. And then the way we have analyzed the potential is that we have had you could say different strategies by turning off the heating for a period in peak periods. So this means we have the morning peak and we have the afternoon peak, or the evening peak of energy. And in these periods we have shut off the heating in order to reduce the load of these buildings. And in some cases we also seen could we actually improve this by preheating the building maybe from 22 to 23 degrees before we have a period where we shut off the heating, if that can improve you could say the energy storage capacity. But yeah, the difference is not that big. But anyway, the results are that we can actually, here are the results for the different archetypes of buildings. And you can see if you look at the individual houses, it's actually the houses from the 60s and 70s which have the highest flexibility potential or demand response potential per house. It's also these houses we have most of, so around 150,000 houses of this type. And then we have estimated what would then be the you could say the total flexibility potential of these single family houses, and how much flexibility could they contribute to the supply grid. This is only dealing with the houses connected to that are not connected to district heating or gas grid areas, so it's around 20% of all residences. But actually we have of course the similar you could say flexibility potential for the houses connected to district heating, and this will become important as the district heating systems are converted from the present biomass or fossil fuels into heat pump production. So for a summary, if you look at the building as a battery, of course we can have additional storage capacity if we use our hot water tanks. Typically the hot water tanks for domestic hot water is quite dumb, and there are not a possibility to utilize the demand response potential in those, but these are things that we are looking into to improve. If we are going to improve the thermal the time constant of the building, of course you could have an inside or insulation from inside, and this will of course increase the time constant, but will typically also decrease the thermal capacity. So it's much better to have outside insulation because this will maintain the thermal capacity and at the same time increase the time constant. But of course, in order to exploit it, we need to have control strategy, and in the buildings, this control strategy needs to react on some signals from the grid. These could be price signals when we have maybe a lack of renewable energy production, or we have some peak power situation. The challenge in that is that if everybody react on the same signals, we would actually maybe just move the peaks to other periods. So therefore, it's important also to have some, you could say, signals that make sure that these demand response activities are not done at the same time in the whole building stock, but in a way is distributed in a clever way, so we achieve, you could say, the optimum demand for the energy system. Finally, of course, changing or cutting off a heating system for 2, 3, 4, 5 hours, of course, that needs to be accepted by the users, and they need to understand that if there is a decreasing temperature, it is maybe because it's expensive to heat, or there is a lack of energy, and this is the reason. But it will come back again later, and this is of course a new experience for end users, and we need to be very clear about these solutions when we introduce them. Thank you.
Okay, thank you, Per. Very comprehensive presentation of energy flexibility. And we have one question for here that for the speakers, Martin asked that you have any experience of using heat pumps as a frequency reserve markets. So how do heat pumps behaves in this frequency market?
Yeah, we don't have any experience on the use of heat pumps in the frequency market. No.
I cannot see any questions, but I can ask you that in the Finland there's a lot of discussion about hydrogen and power to X, and how you see that in your Danish conditions, hydrogen.
There is also a lot of discussion in Denmark of these green fuels in the production of those, and there are also being established some, you could say, test production sites for this. I think the challenge is right now that our electricity system is not 100% renewable energy. So this means if we increase the demand by increasing the production of green fuels, then this will actually increase our emissions quite dramatically, because the efficiency of these production facilities is relatively low. So as it looks now, where we don't have 100% renewables in our electricity system, it would be better to use fossil fuels in our transportation than to use green fuels, because the production will lead to considerable increase in emissions.
Okay,
in Denmark, in the plants, if we are looking into the plants, then it will not be until 2030 where we have a balance between production and demand of electricity by renewables.
I have one more question about this energy markets, like Nord Pool markets, that if we are able to cut, for example, 10% of peak power, it could be meaning some cases 50% reduction of energy price. So have you merged this Nord Pool price tariff there in your calculation there?
Yes, we have used the Nord Pool prices, but of course it was for 2020 and not the price levels we have today. But we can see in Denmark, actually, as a consequence of this, we can see, first of all, that our electricity and gas consumption has decreased with something like 15% compared to last year. And what we also can see is that people actually have moved a lot of their electricity use from daytime to nighttime. So there is a clear we can see a clear change in the profiles I showed you, that people actually are reacting to these differences in prices and are moving their consumption to nighttime, where we typically have lower prices because the demand is lower.
Okay, I have still one question about, you saw this time constant there, And if we cut the peak, how many hours we are surviving in the winter time, thermal comfort, if we cut the peak, how many hours in your calculation is there?
For old houses which are not very well insulated, it's just only manageable 1 or 2 hours. For our new residential buildings, we can actually cut the heating for 15-20 hours without reducing the temperature more than 1 or 2 degrees.
Okay, thank you very much, Per, and I know you have to go to other meetings once more time. Thank you very much, and we have to move on in the program. So we have next speaker is Martin. So floor is yours.
Thank you for the introduction, Risto. So some time ago, I proposed title Data-based identification of energy-saving possibilities, but today I mostly focus on data and identification of energy-saving possibilities. I leave it to you in the audience. So let's see if I can, yeah. So the problem that many real estate owners have at the moment is that it's difficult to grasp the energy performance of their portfolios. So how large is it? How much energy does it cost? Maybe that they know better. But then are their buildings performing well? What's the indoor environment quality? And finally, today, the most important question, what are the energy saving possibilities? So they basically see some letters and maybe some graphs, and that's it. I suppose most of you know that very often the measured energy performance of buildings is a few energy performance classes worse than was predicted. So here are just some examples from Finnish buildings. So in the bottom row, the first one is calculated energy performance class, energy performance level, and then on the right, it's the same building but measured energy use, and it's BE, AD, 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 and then one building that has both A's here. So it's typically three classes worse. But it's quite often to put your finger on it, what is the reason? Is it because the building is used differently as assumed in the calculations, or is the building really inefficient? And for that, we have a project. It's called DigiAudit, this one pilot project of Finnish Center of Smart Cities. And it's our goal is to do, let's say, nearly real-time monitoring of energy use and indoor climate. And the final goal is to really put the data that we gather, to analyze it and put it into context so that these typical users of the platform, for example, facility managers, executive staff, energy auditors, etc., could really implement it in their activities, and also put a link to the project description. But in general, it works so that we gather weather data, energy data, indoor climate data, and then also data from the main meters of energy companies. It's put into a database, analyzed, and then results are presented in a user interface. It's, as I said, it's an ongoing project. It started in 2021 and ends before summer next year. And that's basically the main reason I'm not talking so much about energy saving possibilities, but more about data, because for now we have maybe 1 month of data running from pilot buildings. But it's our university, people from civil engineering and architecture are working together with data scientists and IT people. And of course, crucial. We need crucial is collaboration with our university real estate department, because they are eventually the end users. And then we have also the cities of Tartu and Tallinn as collaborators. We have total 45 pilot buildings, mostly educational buildings, university buildings, schools, kindergartens, but also some offices and social buildings. But what happens? How is our platform and architecture of this analysis? So, as I said, firstly, we need to gather data. So, of course, energy use, so energy meters from buildings, sub-meters, but also energy use data through energy company APIs. Then also weather data and also some information about buildings, because kilowatt hours or megawatt hours only without knowing what the building is don't really give that much information. And that we get from Estonian Building Registry, but also the building users need to supply some information. Then, as I mentioned, indoor climate is also in our focus. So we get information from sensors, and there's also a possibility to get occupant feedback from QR-based questionnaires. Then we get data. Anyone who has worked with measured data knows that it's not 100% reliable. So there we basically have three algorithms. So it's gap filling, both when you have non-cumulative data, for example, room temperature, CO2 levels, but then also filling the gaps in cumulative data, which are basically the energy meter readings. And then finally, we have to assess how good is the quality. Do we get correct readings from the sensors? And I will focus on that a bit more later. Then it's also useful to know the profiles of the building. So when building is designed, some profile is assumed, but we also try to identify the usage profile based on electricity use patterns. And also that is needed for example, some energy auditor for calibrating their simulation model. Then we also need to assess when is building occupied, because if nobody is in the building, there are no dissatisfied persons and indoor climate is perfect. And finally, also how are the systems used? And then finally we get to these outputs. So it's indoor climate classification or assessment, then also energy performance information. So what is heat energy balance? We need to normalize the data, and then finally also assess it through, for example, energy performance classes. And what we think will eventually be maybe the most useful function is putting in the data into context or benchmarking, which I will also talk a bit more later. But to give you an example, what is the typical situation in buildings? So here you see the energy performance classes, more or less, of Tallinn or Tallinn University of Technology buildings. And you see that, well, almost 75% of the buildings based on measured energy use have class E or worse. And currently the new buildings need to achieve class A, and in around 2010 or 13, they had to reach class C. So situation is not very nice. But we also have two class A buildings, which by Estonian definition are nearly zero energy buildings. And here they are. So this is our new laboratory building, and this is the other nearly zero energy building based on measured data. but well, obviously everyone can see that it's not actually an energy efficient building, but it's just a building that is not in use anymore. So measured energy often does not mean energy efficiency, and sometimes also vice versa. I will also give you like a brief example of the one study building. So it was built in 2009. So designed before really energy performance requirements for buildings were implemented in Estonia, and it's quite large. And it's like mix of classrooms, auditoriums, but also offices for researchers. And here is the energy balance. So it's delivered energy and then primary energy, where these values have been multiplied with energy carrier weighting factors. And in Estonia, when we calculate or assess the energy performance, we include space heating, air handling unit heating, domestic hot water. Then this other electricity largely is appliances and lighting, then also fans and space cooling and air handling unit cooling. But then we also have servers. The IT department is in that building. Then we have also large canteen, so kitchen electricity, and then there's also like a garage ramp which is electrically heated, and then there's also the kitchen ventilation system. And these are the ones that usually are not accounted for when assessing the energy performance of the building itself, but they are present in the measured data. And the Estonian legislation allows subtracting these energy uses if you have measured them and when you want to issue an energy performance certificate based on measured data. And here we also see the scale, and if we subtract these values, then from G class we get an F class building, so slightly better. But let's assume that this part, which is like accounted for mostly, maybe there's something else here. If this would be 100, and then it would be class A building, and then we would add this roughly 60 units, then we would end up in class D. So 3 classes worse, as I showed in that second or third slide. So these non-EPBD energy uses have much more effect when we issue the energy performance certificates for new energy efficient buildings. And it's very important to understand where is the energy going, and then you can start making decisions like what do I do to save energy. And then putting it into context, we have developed a solution that when we compare single building weighted energy use against the distribution of weighted energy use of buildings of the same type. And then we get a distribution curve. And for example, if the weighted energy use is 200, then we can see that 54% of the buildings perform better than this building and 46 perform worse. And this can be applied for on system level or also for different building levels. So this is maybe something that building owners grasp better when they want to know how my building is really performing. And now I come to indoor climate assessment because I believe that energy savings cannot come on the account of indoor climate, and therefore we need to be sure that when we do something, we don't compromise or get a penalty in indoor climate. And typically, when indoor climate is assessed, it's based on measured room temperature and, if possible, also CO2 level. And as I said, then we need to pre-process raw data, assess occupancy hours, take into account only the hours where people are there, and then we can calculate the distribution of these values when they are in certain indoor climate classes. So 1, 2, 3, 4. But this, what I put here, is like quite nice data, but the reality can be different. But what can be then the applications of this indoor climate? So people are very much talking about energy cost at the moment, but I think it's very important for building owners, especially in office or commercial buildings and schools, to see what is the effect of indoor climate on their work and study performance. So I suppose many of you have heard that ventilation has significant impact on work performance and also study performance. And if you compare it to the cost of energy, then it's very, very large. Then in COVID, I don't know how it was at your home countries, but in Estonia, but I think it was Riva's official guidance that if you're in school, if the CO2 level raises to 800, then you should open your windows or put them in airing position. If it increases above 1000, then you should end the class. And then when we look at the data, we see these values. So this here is roughly 1 month. And you can see this is 1 week, 2nd week, and all of a sudden these values all drop. And then when we do automated or just CO2-based indoor climate assessment, how do we use this data? So this is basically actually auto calibration of the sensor. It just manipulates its values so that the minimum values are around 400, which is the outdoor level. And then we also have seen from a school measured values, they almost never drop below 800, except for these 2 outliers here. And now when you think that people go to class and they see the CO2 level at next to the door and it's already 800, then you have to open the windows to airing position straight away, and very quickly, if you follow the rules, you have to leave the class. So this like poor quality data can cause problems. Then what we can also do this with this indoor climate. Here you see CO2 values measured in an auditorium in Thalfeldt. And when you see these small fluctuations, that means that the classroom was in use. Blue values correspond to the time when the fans were on, and the orange values correspond to the time when the ventilation system was shut off. And we also see that rooms were used according to the time schedule when the fan was actually off. So the green area is when the fans were on. So this automated assessment enables optimizing the fan schedules to see if there are these peaks, or then you can also compare your ventilation use with occupied hours. And what we also have seen the same example, 800 ppm base level, when you have a variable air volume ventilation system or demand controlled ventilation. Quite often you use this control principle that the airflow rate changes linearly between minimum set point for CO2 level and maximum. And if the measured value never goes below 800, then depending on the set point, you can very easily ventilate an open room when the air handling unit is working. And again, this wastes energy, and there's, I believe, a huge energy saving potential in these cases. Luckily, or I don't know, unluckily, in this building there is no VAV ventilation. Then also, as I said, if there are no people in the room, then there are no dissatisfied persons, and indoor climate is perfect. So the CO2 levels also enable assessing the occupancy of the building. So here there is an algorithm that when this is green, it sort of decided that the room was occupied. And when we compare it to this standard profiles, it's quite okay. But when we have some holidays in the school, then if we include this data here in the analysis, we also get maybe not so adequate picture of the indoor climate. But if there are no CO2 sensors, we think that we can also assess the building occupancy based on electricity patterns. I did not talk about temperature, but that is mainly because quite often we get quite quick feedback if there is problem with temperature, but not so often if there is problem with ventilation. So to summarize, we believe that data-based approach enables to understand the performance of a building and to assure good and healthy working and study environment, also to reduce unnecessary energy use of HVAC systems. And when we look at the whole portfolio level, then also plan some real estate renovation or actions to improve the energy performance. But for that, we need to collect enough data and assure that it's good quality data, and do the analytics and critically assess the results, and eventually, which is probably the most important, and for researchers or HVAC engineers, present the conclusions in an applicable manner to the interested parties. So most important slide, the supporters, and thank you.
Okay, thank you, Martin. I cannot see any questions or comments in the chat, but maybe I can ask you what you mentioned quite at least a couple of times, this quality of the data. And what is your experience, the quality of the data, what you have using in your test buildings? That what is the quality there?
It's usually okay, but then we see very strange CO2 levels sometimes. And then we see schools where they have around 60 degrees Celsius in the classrooms. And to our knowledge, it's not a sauna, it's a classroom. So there are issues. Sometimes, and they definitely need to be identified. So I don't know, maybe next time I can present something. So when we do indoor climate assessment, then, for example, this baseline correction of CO2 sensor, so that affects the results to some extent, but I cannot generalize because in fact we don't have any buildings without mechanical ventilation. So we have quite okay buildings.
Did you analyze in your study how the facility management use this data, or are they just looking for alarms there?
Well, we do not present so many alarms. Our own university real estate department person is attending the meetings when we are developing the platform, but we aim to present the user interface. It's under development, and present it to the city facility managers by the end of this year or maybe early next year, and then we will get feedback. But we try to, well, we will see.
Yeah, but I'm meaning that if you're looking for normal building in Estonia, how well this data is at the moment utilized in the facility management?
Not really. It's like typically they react to complaints, not and not so much on those hundreds or thousands red exclamation marks.
Okay, that's I'm afraid. Also, it's the same situation in many countries. Okay, thank you.
But that situation is becoming better because now the executive level is pressurizing the facility managers to do something.
Okay, something positive. Okay, but thank you, Martin, and let's move on for the third speaker. We have Kenneth is the next one.
You have to open your microphone, please.
It's not.
No, we can hear you. Oh, not yet.
We cannot hear you. Your microphone is muted. We can see your presentation, but your microphone is not open. Just a couple of minutes ago, we can see your slides. It's not open, closed. Maybe now it's open. If you say something.
Now it's open. I'm going to open my presentation.
Okay, perfect.
I couldn't get to my mic when the presentation was on. I hope it's.
Now everything's working very good.
Everything's working good. My name is Kenneth Ahlström. I'm an environmental and energy manager for the housing company Kopparstaden. Kopparstaden is fully owned by Tallinn Municipality in Sweden and owns and manages about 6,000 apartments. My presentation is about showing the possibilities to create a small district heating system outside the central city. And it's something that's not easily done, but it can be done, and we have done it. So that's what I'm going to talk about. Shortage of electricity is nothing new, as seen in my next picture here. The left picture is from the State Electricity Rationing Board in Sweden from 1970. We had a shortage of electricity in the end of the winters when there was little water in the hydropower dams. They had to urge people or force people to use less electricity in Sweden. And the picture on the right, there's announcement from Swedish Power Grid Association from this last February, talking about when one of the biggest nuclear plants was temporarily taken out of operation. We had a problem with getting enough electricity in the southern part of Sweden. We had to import around 2,000 megawatts of electricity. So it's not a new thing with problem with electricity. But after the 70s, to solve the problem, there were 12 nuclear reactors was being built between in the end of the 1970s during the 80s, and that instead created a situation where we had a lot of electricity in Sweden, but the demand was almost the same as before. Therefore, many houses were built with direct electric heating because it was an easy and cheap installation, and with a low price for energy used, it became very popular. We did not have the same trading system that we have today with electricity, and not so much connecting cables to other countries like today. Therefore, prices were predictable and low in those days. But today, it's a different situation over again, when only half of the nuclear reactors are still in use. The trading between Sweden and other countries is expanding, and rising population and increase in the housing stock. With all that in account, we are back to the same problems we had in the early 70s, and sometimes with risk of shortage in electricity supply, which my next picture will show. It's two pictures from the Swedish Power Grid Association's homepage. They show electricity production figures momentarily in Sweden. On the left, the chart on the left is a day in December 2021, 16:13 in the afternoon. -8 degrees outside where I live in the middle of Sweden, and it was -degrees in all over Sweden that day. The wind power was producing poorly. There was not much wind, only 1,397 megawatts at the time. Around 10% of installed power was in use. Sweden had to import 2,344 megawatts at that time. And if you look at the right chart, it was over a month later, it was +6 degrees outside the same time in the afternoon. The wind was blowing. We had over 9,000 megawatts of wind power in the system. Over 70% of the wind power, installed power was in use. At that time, Sweden could export 5,473 megawatts. And you can see on the consumption, total consumption in Sweden, when the cold day was 25,370 megawatts at the time. And on the warm day, the consumption was 5,000 megawatts lower. And the reason for that is cost of difference, mostly because of electrical heating in buildings in Sweden. So heating with electricity causes big problems. That's why it's important to reduce heating by electricity, because we will have better use of electricity for transportation and industrial purposes in the future. So that leads us into district heating systems, which could help us reduce electricity in the heating sector, and therefore better stability in the electric grid. Here is a picture of Sundborn, a small community outside Falun with about 1,000 inhabitants, and maybe 500 households or less. Kopparstaden currently owns and manages 20 existing apartments in Sundborn, and we have 24 apartments in production. These are the 4 red buildings in the forefront on this picture. Half of the apartments we had earlier had the electrical heating, direct electrical heating, and the rest were up until now had used a heat pump for heat and hot water. And on really cold days, we had an oil boiler was also started when the heat pump didn't manage to keep the temperature up. The heat pump in the old buildings had been used in use since 1995 and was functioning worse and worse. And when we started building the 24 apartments in the red houses in the front in 2019, it was necessary to take a new holistic approach for heating existing and new buildings. And from the beginning, everyone was convinced that we should invest in new heat pumps, and that were no other options for a little community like Sundborn to have any other kind of heating system. But this would have meant that about 50,000 kilowatt hours of electricity would be added to the 200,000 kilowatt hours that we already used in Kopparstaden's building in Sundborn. And as I'm not particularly fond of using electricity to heat houses, so I thought there must be another solution. So I contacted the energy company Kvols Energy and Water, and I also contacted for the municipalities sector service. These are the people that manage schools and other community buildings in Falun. And I planted an idea of a common district heating network in Sundborn instead of heat pumps all over. I also knew that the school and sporting hall was about to get the new heating system in the near future. Also planned to use heat pumps. In the school, they have been running an old system with wood pellets, wood chips heater boiler, and with bad performance. So they have to be running in oil burner also during winter. I called to a meeting, and we sat down in December 2019. And after some discussions, we could see that both Kopparstaden and Sector Service had a demand for heat, and the sum of money that we all anyway had to put in a solution for heating. Whether it would be heat pumps or a district heating system, we had the money, so we had the opportunity to do something together, maybe if we could get the right cooperation between us. The first reaction were that maybe the base for district heating in Sundborn was too small, but when Kvols Energy and Water had looked at the different alternatives and received quotes, we found a solution that involved about the same total investment cost as a new heat pump systems in different places around Sundborn. Maybe the initial cost should have been lower if we had heat pumps, but over a life cycle cost, we could see that there would not be about the same amount cost for maintenance and everything. And with today's prices of electricity, this calculation has been even better. So said and done, the ball was rolling, and a new district heating system was going on in Sundborn. And this picture is an overview, an outline of the district heating system. It's about 700 meters long initially, so it's a very small system. But the dimension is enough to expand the total length, maybe double the length, and to collect other buildings also to the system. System uses ordinary steel tubes with isolation, as seen on this picture at the right. And on the left, you see the old heat pump and the oil boiler in the yellow house in the middle, that was used for our old buildings in Sundborn. These are gone now, and we have clean, nice system without with the heat exchanger taking up a tenth of the space in that room today. The primary temperature in the district heating system is around 75 to 90 degrees Celsius, depending on actual power demand for the moment. And here's a picture, some pictures of the actual boiler plant. It's a prefabricated plant from a firm called Bioptima, who has produced this building. It uses fuel is wood pellets produced in Kvols Energy and Water's main plant in Falun. And there is also a backup boiler with 450 kilowatts power that uses bio oil for fuel. Normally, backup will not be needed only in the cold days or if there's a problem with ordinary biofuel boiler. Ordinary boiler has a maximum power of 350 kilowatts, so it's quite small. I told you it was a small system. It's one of the smallest, I think, in Sweden. And interesting is this is the picture where the wood pellets used in Sundborn is coming from. It's the Västermalmsverket in Falun. It's called. It's the district heating plant in Falun where they produce 20% of electricity needed in Falun. It comes from that plant, and 375 gigawatt hours of district heating also from that plant, heating almost every building in central Falun. The picture on the right, you see two big barns along the road there. These are where the pellets who is produced in the alongside the heating plant is stored and dried during the summer. Some pellets are used summertime, but mostly the pellets are used in winter in Sundborn and 3 other heating systems outside Falun. And you can look at these barns like 2 big batteries accumulating energy from summer to winter time. So it's a very smart system producing wooden pellets for use in the winter and accumulating over the summer in these barns. These barns also have a big solar plant on the top of the roof, and the electricity from the solar panels are used in the process for producing the pellets. We also have a data center next to the power plant here, and some excessive heat from the cooling the service are also used in the process. So it's a quite complex and system is very smart, I think, for using all excessive heat in the energy system. And what we are today, today we have some work in progress. We are connecting 12 more apartments out in Sundborn during this winter. So the net has the pipes and the tubes have grown about 200 meters from these 700 meters we had from the beginning. So it's an expanding system, and I think it's going to be even more longer when other houses in nearby want to connect to this system. So if I'm summing it up and the results and conclusions of what we have done in Sundborn together with Falun Energy and Water and the sector service, is that it is possible to build a district heating network in a small community if you can cooperate and collaborate with others and get together a base big enough to get economy in the whole project. Kopparstaden reduces use of 250,000 kilowatt hours electricity annually, and if you sum it up with the other that are connected to the system, it's around 500 kilowatt hours that we reduce dependency on electricity in Sundborn. So from 500,000 around 500 households is also 1,000 kilowatt hours less energy consumption in Sundborn because of this system. And the key is everyone wins in this, but the biggest win is for the environment, I think. Thank you.
Okay, thank you, Kenneth. Unfortunately, we cannot see you. Your video is not working. I don't know. Have you closed that? But I cannot see any questions in the chat. But if I asking you this by your no, now it's okay.
Okay.
Now you are live.
Yeah. Okay.
how you see this bioheat? Is that one big solution in Sweden, or
what did you say?
Because in the future, can you still extend the use of this bioheat and pellets there? Do you have available bioenergy available there in Sweden?
Yeah, I think so. Of course, we have to. I mean, 90% of the Swedish apartments are connected to district heating systems, and not every one of them are using biofuel, but very big. Many are using that, but there's a limit in how much you can use. But if you at the same time make efficiency measures in houses and keep down the use of energy, so I think we could connect more to this system, and it's not what I say, it's not possible to keep installing heat pumps in Sweden or in Europe, the rest, I think, because we have problem already with electricity and the power output, and the transportation and industrial projects are going on with electricity would need that energy better, I think. What we use in the district heating systems are mostly waste. In Falun, we have waste from the forest industry in that plant. There's branches and tree tops, and there's sawdust from the tree industry around Falun that's used because both in the big plant in Falun and in the pellets production. So this is waste that these branches and tree tops would not have been used if we didn't have a production plant in Falun, I think. And 20%, as I did, 75 gigawatt hours of electricity is produced in the plant in Falun, and this electricity keeps the pressure from the network in the power grid system around Falun, because it's produced inside Falun and used in the local net. So I think that's very important for the future.
Okay, thank you, Kenneth. And I think we have to move on, and we have still one talk left, and Timo will talk about next of simulations, optimizations of buildings with the simulations.
Yes, thank you, Risto, and good afternoon, everybody. The contents of my presentation are here. First, a brief introduction, then I will talk about our solution to optimize energy renovations, and our solution for that is a tool called AI Energy Survey. And at the end of my presentation, I will present some examples of results and what benefits the building owners get from this type of analysis. Okay. We talked already today about the energy crisis. Everybody is aware of that, and that makes the energy efficiency projects even hotter topic. I think everybody in the audience knows the benefits that energy efficiency projects produce, which are lower energy costs. In most cases, you get life cycle cost savings. When you perform an energy efficiency project at the same time, it affects your maintenance backlog. Many cases you get improved comfort, better indoor conditions, and one other measure for the property owners is the enhanced property value. One important factor is the lower CO2 emissions, and with energy efficiency projects, you can drive towards sustainability goals. And one latest aspects is the EU taxonomy, which is a classification system for environmentally sustainable investments. And the aim of it is to link the availability of funding to how sustainable the investment is. And our solution for building owners to tackle these issues and to make analysis for the entire property portfolio is a tool called AI Energy Survey. This infograph shows the process, what we do with this tool. So we can analyze a single building or entire property portfolio. The idea is that we read information from the energy performance certificate, currently only Finnish energy performance certificate, and make a simulation model based on the data in the certificate. Then we define energy efficiency measures that can be applied for that particular building, and then we calculate different alternatives, different energy efficiency measures, different combinations, and finally get an optimized result. Best energy efficiency measures with the best life cycle cost savings, CO2 emission reductions, and also related to taxonomy targets measures so that the taxonomy targets can be reached. So in this tool, we combine artificial intelligence in reading the data, then building the simulation model, use our databases that we have collected over the years for investment cost, for example, and then basically we do mobile optimization, multi-objective building optimization. Of course, we don't do the machine do everything by itself. We have always some expert looking at the results that they are feasible. We don't want to put the ground source heat pumps in a plot where there is no space, or if there's an aquifer, or we don't put boreholes in the city center and so forth. So we make sure that the solution is feasible. Of course, this is a desktop study, so we don't do site visits. So and there might be some extra gain if a site visit was done. So with this tool, building optimization is faster than ever. This tool drastically reduces the cost of computing. It is our own software development. It doesn't rely on any commercial tool. And the strength is that you can in a fast way analyze the entire property portfolio. The largest project we have done consisted of 1,500 buildings. The software is significantly faster than any other software for multi-objective optimization. This is because we simplify some things. We don't model all the details of the building. The simulation model is created automatically. This is the simulation is done at 1 hour resolution. Of course, the results, if we look at a single hour, the results may not be as correct as with some other software. But if we look at the annual energy consumption, the result is very accurate. So in this tool, we employ methods based on energy simulation and artificial intelligence, and thousands of energy optimizations can be done in just a few minutes on a laptop. And AI is utilized in reading the data in the energy performance certificate, in building the simulation, and in the definition of the investment costs. Okay, this slide illustrates some data in the Finnish energy performance certificate that we use in the tool. On page 3 are the most important data areas of building envelope, the U values, then window areas, directions, information about ventilation system, heating system, cooling system, domestic hot water, and so forth. And this information is read in the software automatically from the PDF of the energy performance certificate. Also, the text here, the text matter, for example, in this case, it's heating is with pellets, so that affects also the simulations of this. And also there is some electrical heating in bathrooms. So that information is read also and taken into account in the simulations. So when it comes to functionality, AI Energy Survey is pretty similar to leading commercial and open source software like IES and so forth. With this tool, we can analyze the property energy efficiency potential. Basically, after the simulation model has been created, is mobile optimization. But currently, we don't employ any optimization algorithm because the simulation was so fast. We just do brute force calculation. We can also create a new energy performance certificates and on top of that run the energy efficiency analysis. And we can take into account in the analysis the usual measures that are done when doing energy optimization, so structures, ventilation systems, different heat pump systems, solar energy, wastewater, heat recovery, condensed heat, and so forth. So then a few examples of results. This is a typical plot what you get when you run a mobile optimization. Here you have the initial situation on the lower right hand corner where you have the high energy consumption, and our goal is to lower the energy consumption and end up to that left corner with the low energy consumption and hopefully low life cycle cost, which is illustrated on the y-axis. Typical results for an individual buildings are shown here. Of course, depending on a building type, they can be slightly different. This is an apartment building, and we can see that with the heat pump systems, we can save a lot of energy. Structures, which structural renovations, not so much. An interesting graph for the costs that the building owners are interested in is that how large an investment is required to save 1 megawatt-hour of energy. And here we can see the superiority of heat pump investments compared to structural renovations. Then for the entire portfolio, the results can be something like this. There are about 25 buildings listed here. And for each building, we give the life cycle cost saving, the required investment and savings in heating or electricity. And then here is given the optimal energy efficiency measure. In many cases, it's some heat pump system, ground source heat pump, or hybrid heat pump, which consists of exhaust air heat pump and ground source heat pump, in some cases also the windows are renewed, and the numbers here refer to the power of the heat pump system. Then CO2 emission reductions. The life cycle cost savings, there are savings if this number here is positive. These are for apartment buildings, so the savings are not so huge. But if we look at the office buildings or commercial buildings, then the life cycle cost could be very large, and payback time even 5 years. For taxonomy analysis, this is a typical figure how we can illustrate the key parameters for taxonomy. Here we have approximately 30 different buildings in a building portfolio. Each set of bars shows the current E-value with gray color, and then yellow, red, or green color illustrates the level of E-value that has been reached after energy efficiency measures. And these dashed lines show the national top 15% or 30% thresholds, below which, depending on building type, the E-value should set in order to reach taxonomy goals. And in this building stock with reasonable energy efficiency measures, most buildings reach the national top 30. A few can go below 15%, but there are also buildings with which it is not possible to reach the threshold set by the taxonomy requirements. So to conclude, what kind of benefits building owners get from this type of analysis? AI Energy Survey provides time and cost-effective screening of entire building stock. With previous or other methods, it would take dozens of times more time and money to produce similar results. With this kind of analysis, we can identify easily most potential buildings to which focus further studies and measures. AI Energy Survey can provide roadmaps for carbon neutrality and taxonomy, and this analysis also gives information on current status and potential to reach taxonomy compliance in the property portfolio. That was everything I had to present. Thank you.
Thank you, Timo. And we have here a couple of questions for you. And first is dealing with this energy certificate and how you collect the data or how you utilize that, because they are coming some kind of documents. So how you use this data in your tool?
So we need to have the data, the original PDF document of the energy performance certificate, and this we can get it from the property owner. So this information, what I showed you earlier, all the areas or U values are given. They are not public information.
So you manually fill them or matching?
No. It's automatic. When we get the PDF document, then we just read that in the software, and there is no manual work needed in that.
Yeah, there is also continue of the question that how you assure the quality is okay, that the certificate data is correct.
Yeah, of course. We, based on our experience, we can see if there is if some area is maybe 10 times larger than it should be. But we have noticed that in many cases in the certificates there are errors. There are people who are doing the certificates. There is a big variation on quality. Yes, and finally in the results, if there is something very strange, we can notice it. But yes, of course, we need, if our analysis based on the data in the energy certificate and that is erroneous, in some cases we can't do anything.
Okay, there's also a question about the economical calculation, the investment cost information, and where you're getting those data. Yeah,
well, at Granlund we have a long experience of doing energy efficiency projects, and we have a large database of cost, real life costs from past projects, and a database from equipment manufacturers and so on. So that's where we get the investment cost data.
Okay, then there is a question about a little bit about this energy certificate, and can you explain, Timo, a little bit about this process in Finland, this energy audit, and how that happened and when that happened in Finland?
You mean
energy certificate? How or why the building owner do it that, or when they do it that?
So the energy performance certificate is a mandatory document.
Yes, mandatory document that is based of that, because I think the question here that how does the information get in the PDF? What you mentioned, this energy certificate.
Yeah, so each building needs to have a certificate, and a certified person needs to do that certificate. So usually the person uses drawings and technical documents of buildings, and also does site visit.
But technically it's needed when you want to sell or rent a building or houses there, you needed this certificate.
Yeah. Yes.
Yeah. Okay, thank you, Timo. There is in the chat one question for Kenneth, and I think if you Kenneth open your microphone. I think it's dealing with this bio burning and CO2 emission of that, and if we compare this bio heat for electricity, is meaning that can you compare for this CO2 emissions?
Yeah, the question of CO2 emissions for electricity is all over the place, I think, depending on who you ask. If you use that electricity to reduce coal burning in Europe, it's very expensive and valuable to get that electricity to someone else. And if you use leftovers from the forest industry, that's if you don't take care of it, it will be left out in the forest and they're lying there and emit emissions. So the better way to use it is to use low low quality energy for warming houses, and they use electricity for maybe export it outside Sweden to countries that have worse emissions for electricity. You saw the slide where we had warm weather in Sweden, we could export outside. When we had cold weather in Sweden, we had to import. And the question is, and that's because we have heating with electricity. So the question is, should we get that electricity from? Should we import it from Poland with high CO2 emissions, or should we reduce the use of electricity for heating? That's the main question, I think.
Okay, thank you for for this answer, and I think I cannot see any more questions here, so I think we are maybe coming in the end, and I would like to thank all the speakers and also the participant, and also I would thank for the Siru behind of the machine room there handle and make this possible, the whole webinar. And I will close this session now, and if all the speakers stay online a couple of minutes so we can have some words. Thank you very much for everybody.